All right, everyone. Chapter 16, Acid-Base Chem. I am hiding from my children, and they are playing downstairs. So if you hear random screaming, they're fine. And they are under adult supervision. So here's week 11 and 12 homework problems. Obviously, they're in mastering like they always are. So there you have those. All right, you guys. Acids and bases. These are words that we use quite often, actually, and they are a very significant part of our lives, our day-to-day. You know, we eat them, we clean with them, we use them quite often, so we should know what they are. Acids, if you think of like citric acid, so lemons, limes, oranges, all those citrus fruits contain citric acid, and that's what gives it those fruits sort of the sour taste that they can have. Acids can be used to clean metals, and they can also neutralize bases. So when we talk about neutralization reactions, we are going and taking a base, adding an acid, and getting a water and a salt. And so you go from an acidic solution or a basic solution to one that's pH neutral because you've just made water with a salt. And then bases have a bitter taste. They feel slippery, so they feel like soap. You use bases for a lot of your cleaning products in your home, and they neutralize acids, so they can go the other way. So here's some just different acids and bases that we have around our house that you see all the time. So there they are. All right, you guys. So what we need to do is sort of define them in a more scientific way and talk about what they're actually doing and why are acids and what makes a base a base. So a strong acid is one that dissociates completely in water. So there is no equilibrium. It just goes 100% to completion. This is something, I don't have a lot of things that you just need to know, but these you need to know. So you want to memorize the strong acids: HCl, hydrochloric, sulfuric, nitric, hydrobromic, hydroiodic, and perchloric acid. Those are your strong acids. There's another one, it's a hydronium ion. It's also considered a strong acid. So all of these things are going to dissociate 100% in water. So if I have 1 molar HCl, that means I have 1 molar H plus and 1 molar Cl minus, because they are going to separate and mingle in the water, but they separate completely. So anytime you have a strong acid and you throw it in water and I'm looking for the H plus concentration, it's going to be exactly whatever you put in solution. Those are always easy questions to answer. So that's what a strong acid is. And a strong base is the same thing. It dissociates completely in water. Strong bases are usually the group 1 or 2 metals. So your alkaline earth metals with hydroxide. So you get sodium hydroxide, potassium hydroxide, lithium hydroxide, rubidium hydroxide, barium hydroxide. Some of them are not soluble, so they are not considered strong. But anytime you have a metal, a representative element metal, so 1 or 2, with your hydroxide, that's a strong base, and these guys dissociate completely in water. So again, if I have 1 molar NaOH, that means I have 1 molar Na plus and 1 molar OH minus. So if I'm looking for the concentration of OH minus, I just got to look and figure out what the concentration of my base that I put in there was. And those, again, are easy questions to answer. So there are different ways that scientists define what an acid and what a base is. There's Arrhenius, Bronsted-Lowry, and Lewis. I'm going to briefly talk about the Arrhenius definition. We're going to spend a lot of time on Bronsted-Lowry, and Lewis I don't really go into. They're all essentially saying the same thing, just in a little bit, maybe of a more specific or different viewpoint. An Arrhenius acid is something that increases the concentration of H+, which is why when we categorize acids, they usually they always have to have an H in front. So HCl, here's boric acid, sulfuric acid. They are going to increase the concentration of H+. So they all have a proton and H+ to donate to the solution. So they're going to increase the concentration of H+, and bases, substance that when dissolved in water, they increase the concentration of OH minus. So we talked about our strong bases. lithium hydroxide, potassium hydroxide. Okay, so they all have OH and they're easy to identify. And they're going to increase the concentration of OH minus when you throw them in solution because they all dissociate completely. The problem with the Arrhenius definition is that there are weak bases that don't obviously increase the concentration of OH minus. Bronsted-Lowry, we're talking about the role of the H plus in the definition. So when we talk about protons, we're just talking about H plus. That's a proton. Because it doesn't have any electrons, it's literally a proton. So anything that's an acid has to have an acidic proton. So it has to have an H plus that's going to separate. If you see something like that, these are not acidic protons because they are not able to detach. These are all covalent bonds. This is a molecular compound. So they're all molecular. So they're all covalently bound. You have to have sort of an ionic component. So HCl. This is more of an ionic bond. And so the H can leave the Cl by itself. So anytime you have like an H that's written out in front, even if you have like acetic acid, looks like that. But this right out in front is my acidic proton that's going to leave. These guys in the middle here are covalently bound to the carbon or to the oxygen. And so they're not going to go anywhere. These are your acidic protons that I'm talking about. The H is out in front. A base is a proton acceptor. So it has to have a place where it can accept that H plus. So an acid and a base are basically, no pun intended, going to throw a baseball, which is your proton, back and forth. Your acid is your pitcher and your base is your catcher. So when that acid releases that proton into solution, that base is going to have a way to attract it, to soak it up. And so one way is if you have OH in solution, you're going to form water. That oxygen has some non-bonding electrons that are happy to accept a proton. You can also have amino type bases that contain nitrogen. And in this case, you form ammonium, right? Because that ammonia has accepted that H plus. That 3 now goes to 4, and now you have an overall positive charge because you've accepted that H plus. So that's our Bronsted-Lowry definition. And then Lewis talks about electrons, but he's essentially saying the same thing. Okay, so with Lewis acid-base theory, we have our acid, our base, and then we have their conjugates, which are on the other side of your arrow, be it your equilibrium arrow, whatever. Your conjugates are always on the product side, okay? And then the acid and base are on your reactant sides. Every acid has a conjugate base, and every base has a conjugate acid. What this is saying is that when the reaction goes forward, okay, the acid is going to donate that hydrogen to the base. And now that acid does not have its H anymore, but the base has it, right? It's gone from 2 to 3. So if we're going into the reverse direction, now my conjugate acid, this one's donating back in order for my reactants to form again when we go backwards. So that's why now what was my base is my acid, and what was my acid is my base. Okay? So what we want to do is be able to label acids, bases, conjugate acids, and conjugate bases when we have these equations in front of us. I'm going to do A, and then you can do B, C, and D. If I'm identifying my Bronsted-Lowry acid, base, and conjugates, I got to look and see what's going on. So I'm going to look, this is water. Water is, and I'll go into this I think in another couple slides, but water is amphoteric, which means that water can kind of be an acid or a base depending on what you need him to be. He's cool with whatever. So we gotta look at who else is with water. So we have H2SO4. All right, we have ionizable hydrogens out here. So we have protons to give. So let's look at what happens to this guy on this side. He looks like he's gone from H2 to 1 hydrogen, so he has donated a proton. So H2SO4 is my acid. So now I got to see what happens to water. So here's water. And water now looks like a hydronium ion because he has accepted that hydrogen from the acid, which makes him the base because he's the acceptor. Right? Donor, acceptor. Now we look on this side. Remember, every acid has a conjugate base and every base has a conjugate acid. So HSO4 is the conjugate base and H3O plus is the conjugate acid of my base. Because if we go in this direction, now my proton's going that way. So we get acid, base, conjugate acid. H3O plus will never be a base. OH minus will never be an acid. I can promise you those two things. All right, pause. Try B, C, and D. Okay, just make sure your labels are right. Remember, this guy will never be an acid. He's a strong base. Okay. Also notice that in C and D, this guy can act both as an acid or as a base depending on what goes on in your solution. Water can also do whatever. So in the first one, water is the base because it accepts that proton. And in D, water is the acid because he's going to donate back. When you have a polyprotic acid, which means you have more than one out in front, like sulfuric acid is also polyprotic acid, they can kind of go either way. Okay, so there are your acids, bases, conjugates. Oh, look at that. So a polyprotic acid has more than one proton to donate. And once the first one is donated, then they become amphoteric, which we talked about a second ago. And so you can predict their behavior. A polyprotic is like, again, H2SO4, boric, H3BO3, phosphoric, H3PO4. They are also going to donate one at a time, and then it's always more difficult to get the second and third proton off than it is to take the first one. Equilib. There we go. Strong acids and bases. So Cl is going to dissociate completely into H plus and Cl minus. There's no equilibrium, there's only dissociation. Whatever concentration my strong acid or base is, that's the concentration of my H plus or OH minus in solution. And the reason why we need to find what these concentrations are is because that's going to tell us our pH. And that's what we care about. My hydrogen ion concentration of a 0.25 molar solution of HCl. Well, if you have 0.25 molar HCl, then you're going to have 0.25 molar H plus. That's it. Again, B, what's my concentration of HCl? Of H plus. It's 2.5 molar because it's strong. Oh, what'd I do there? And OH minus. All right, so now we get NaOH. Strong base. I want to know the hydroxide ion concentration of a 1.3 molar solution. Okay, well, if this is strong, it's going to dissociate completely. So my concentration is 1.3 molar. The reason why I go through this is because there are some questions that are honestly just want you to identify that it is a strong acid. So they will ask you this, or I will ask you this. And you don't have to do any math and you don't have to overthink it. It just is what it is. You just need to identify that it is a strong acid and go ahead and write down your concentration. Weak acids or weak bases. Now we do have an equilibrium, and our math is going to be more difficult. I think we're just going to go into the math like next time. But we need to label the acids, the bases, and the conjugates. But also now we have K expressions because we have equilibriums. So you can write your reactions out this way without water, or add water and write them out this way. I always add water because the base equations don't really make sense without adding water. So I just add water to everything. But if you don't, H plus is the same as H3O plus. So this is also just this. So this is equal to my H plus concentration. So if I ask for H plus, it's the same thing as telling me what the H3O plus is. They're the same thing. It's just how you write it. Again, I always add water because I feel like it just makes more sense that way. Okay, let's look at 3. We got to label acid, bases, conjugates. All right, well, here's my acid because over here it has lost that H plus, which means this is my base, this is my conjugate acid, and this is my conjugate base. Okay. All right, so now I get to write my K expression. If I have an acid in water, it's a Ka. If I have a base in water, it's a Kb. All right, so here my Ka is concentration of F minus times my concentration of H3O plus. I leave out water because it's a liquid and I don't care. So HF goes on the bottom. That's my K expression, my friends. Easy. Okay, just like in the last chapter. Ka is for acid, Kb is for bases. So I want you guys to stop and do this. There it is. Conjugate acid and conjugate base. My base, my acid. Remember, it's products over reactants. There is no stoichiometry, so we don't have to worry about it here. And that's that. A K value here is going to tell you who is the stronger acid or stronger base. So the larger your K, Ka or Kb, the stronger the base or the acid is, because a larger K means there's more dissociation. So if we need to go in increasing is always weak to strong. Sometimes I have trouble with increasing, decreasing because I always go the opposite way. So sometimes if I write it out, it will just like keep my brain functioning. All right, so the weakest acid is going to have the smallest Ka. So that's this guy. So he's 1. Then that guy. Next is 3 is acetic, and 4 is hydrofluoric. Hydrofluoric is the only halogen that makes us a weak acid and not a strong acid. However, HF can eat through glass, so it needs to be stored in special containers. So that's why some people also think it's strong, because it's pretty corrosive, but it's actually a weak acid. All right, you guys. So if you are to identify which acid is stronger or weaker, just look at your Ka or your Kb values. Water is amphoteric, so it can act as an acid and a base, and when it is like hanging out with itself, there's a very small amount of it that will auto-ionize into an acid and a base. So a teeny bit of your water exists as H3O plus and OH minus. And that's just a thing that happens. And so what we end up with is our equilibrium expression for this process is a special value Kw that's just for water. And that Kw is always the same at room temp. It's 1 times 10 to the 14. Always. This is a constant that we're going to use over and over and over again. And it's called our Kw. It's our autoionization of water. So it's your equilibrium constant for water. So that number we need to know. remember that that number is going to be the product of my hydrogen ion concentration, or my hydronium ion concentration, times my hydroxide concentration. So if I know what my hydroxide ion concentration is, and I know Kw, because I know Kw all the time, then I can find H3O plus just by division. And vice versa, if I know my hydrogen ion concentration, I can find OH minus by using Kw, and that's why we need it. Because we can go from one to the other very easily, and sometimes we need to convert from one to the other. Okay, so if we need to calculate OH, if my H plus is that, here's how we're going to do it. Did I give myself space? I did. So we get 7.5 times 10 to the minus 5 molar. Okay, so that's my H plus. So if I remember that Kw is equal to H plus times OH minus, then I know that Kw divided by H plus is going to give me OH minus. So I say 1 times 10 to the minus 14 divided by 7.5 times 10 to the minus 5. And I get OH minus. So that gets me what I want. That is my hydrogen ion concentration. Right there. Easy. All right, guys. Try B and C. Okay, here are my answers. So now we get to identify if it's an acid, base, or neutral. So in the first one, we needed OH minus. So this is my concentration of OH minus that I calculated. And I was given H plus. So what I do is I find which one's bigger. Which is the bigger number. And that's going to decide if it's acidic or basic. So in this case, the H plus is bigger, right? Because 10 to the minus 5 is bigger than 10 to the minus 10. So this solution is acidic. My B is neutral because they're the same, right? They're both 1 times 10 to the minus 7. And in the last one, my OH minus was 2.3 times 10 to the minus 6. And H plus was this one. So this solution's basic because that one's bigger. So that's how you determine acidic, basic, or neutral. You just find which number is the bigger, which one has the bigger concentration. All right, so here's the pH scale. Most people are familiar with the term pH and talking about acidic and basic solutions. So essentially, if your pH is below 7, it is acidic solution. It's considered acidic. If your pH is equal to 7, that's where it's neutral. And if your pH is greater than 7, it's considered basic. But what is pH? pH is essentially the amount of hydrogen ions that are in solution. The reason why it's on a logarithmic scale, if you look here, is because your concentrations can have huge variations. So you can go from, 10 to the minus 1 to 10 to the minus 14. And so those numbers are have a really large variance. So if you put it on a logarithmic scale, the numbers 1 to 14 make a whole lot more sense. And biologists tend to just like to work off this scale better than working with scientific notation. So we put it on a logarithmic scale. So in order to find the pH of something, you're just going to say the negative log of whatever your hydrogen ion concentration is your pH. So the relationship is if you have a hydrogen ion concentration that's 1 times 10 to the minus 3, usually your pH is going to be somewhere close. This is 1, so it's going to be right on the money, to your exponent. And it changes when this number changes. So, as this number gets bigger, if it's 2 times 10 to the negative 3, it's going to be a little bit off from 3, but it's still going to be pretty close. So that's sort of how they're related. And so in order to calculate a pH, you just need to know the hydrogen ion concentration, and then you can calculate. pOH is the measurement of OH ions in solution. So the pOH scale, as you can see from the graphic, is like opposite of your pH scale. So we usually just use pH, but you can also easily find your pOH, which is going to be pretty much the opposite of what your pH is. So they are related by 14 is going to be pH plus pOH. So if my pH is 4, 14 minus 4, my pOH is 10, right? So that's how they're related. So that's a pretty easy conversion going from pH to pOH. And these are added, unlike the kW, which is not added, it's multiplied. Okay. So we want to find the pH and the pOH for the following and indicate if it's acidic, basic, or neutral. Okay. We are given the H+. So if I want to find the pH, I'm going to take, and remember that pH is negative log of my H+ concentration. So I plug that into my calculator, and I'm going to say pH equals negative log of 7.5 times 10. Remember, on your calculator, you're going to use the E button to the negative 5. And that's going to give me a pH of 4.12, which is around 5, right? So there's your pH. Now my pOH, I'm going to get by subtracting. So I'm going to take 14 minus 4.12. So I get a pOH of 9.88. Okay? Okay, is this acidic, basic, or neutral? We always look to the pH to tell us that. And since this is below 7, this is acidic. I want you to do the same thing for B and C. All right. B is neutral because it's pH 7. pOH then would be 7. So that's a neutral solution. And C, we are given the OH concentration. And so we can find the pOH by taking the negative log of that. So now we have our pOH, and then we subtract that from 14 to get the pH. It's a high pH, it's above 7, so that's a basic solution. All right, now we gotta go the other way. Now we're given the pH, and we have to find the H+ and the OH-. Okay, so this is what we're gonna do. So I know that 3.4 is equal to the negative log of x. So what I do is I need to press the second log button, which is going to be 10 to the, and I'm going to say negative 3.4 on my calculator. All right. So then that's going to give me back my H+ concentration because this is the pH. So it's going to be 3.98 times 10 to, that's an ugly 8, and that's okay. And pH doesn't have a unit, but molarity does. So when you get the concentration, you need to make sure you write it. So there's my H+ concentration because that came from the pH. Okay, so now if I need now if I need OH-, I'm going to say, well, remember this, Kw is equal to, so now that I know that, I'm going to say 1 times 10 to the minus 14. I divide by my concentration of H+, and that's going to get me my OH-. Okay, so this is my OH- concentration. Okay, so that's my OH- concentration right here. And I found it just by using my Kw equation. Okay, so I look at my concentrations. My pH is low, so I should have a lot more acid than base, and I do. My base concentration is really low. All right, so try B, try C. make sure all this math makes sense. And you are using inverse log, so this is second log. And then you're going to hit negative, whatever, 12.2, 3.4, 5.8, whatever it is. Okay. So let's put it all together. We can essentially take one value, if you're given pH, or if you're given OH minus, or whatever, and we can convert to all the other ones. If you're given pH, and you need to go back and forth from pH to pOH, you're just going to subtract from 14. We're going to use this relationship here. If you're given pOH and you need OH minus, so if you're given this and we need to go down, you're going to use this remember is second log on your calculator, and you put negative whatever they give you for pOH. If you're going the opposite way, it's negative log of your OH concentration. If we're going from H plus to OH minus or vice versa, we're going to use my KW equation. Remember, this is multiplication. Sometimes people add and subtract this, but you want to multiply or divide for that one. And then the last one, pH to H plus. Again, if you're going from pH to H plus, you're going to use second log, then the negative of whatever they give you for pH. And if you're going up, you're going to do negative log of your hydrogen ion concentration. So we can go from one to the other, and there are multiple ways to solve these problems. Do whatever you like to do. Once you get, two of them, the last one you can usually do there's like a couple options. So do whatever you find easiest. All right, so we want the whole shebang. pH, pOH, H plus, and OH minus, you want all four. So I will do A for you. Okay, so we have a pH of 7.41. Easiest thing is to find my pOH first, right? Because it's just 14 minus 7.41. And that's 6.59. Okay, now we need our concentrations. So since I have pH and pOH, if I take negative log, which is going to give 10 to the negative 7.41, that's going to give me my hydrogen ion concentration. And I get 3.89 times 10 to the minus 8 molar. Okay, so I can go two ways to get OH minus. I can either take KW divided by H plus, or I can do the inverse log of my pOH. Again, it's whatever you like. So what I'm going to do is I'm going to do the negative log, because I don't know, it's like less buttons. So I'm sorry, inverse log, not negative log. Inverse log of negative 6.59, and I get 2.57 times 10 to the minus 7 molar. Okay, so that's it. You just decide how you want to use it. You can use a little diamond if it helps, but I got the other three. Pause it, solve, come back and check. All right, you guys, here's all the answers for B, C, and D. D, I know you get crazy answers, but it's okay because this acid is so strong. It's a 4 molar solution of acid, which is really strong. So the pH is going to be super low, and it's going to be outside the boundaries of what we usually work in, and that's okay. It can happen. So you didn't do anything wrong. So we get a negative pH, we get a pOH that's huge. We have hardly any OH minus in there because my H plus is just so strong. So if you know how to convert from one of these to the rest, you are good to go. If you're having trouble and you think it's a calculator issue, make sure you're using the EE button when you are putting in like your times 10 to those, and make sure you're not just using 10 caret. You want to use the second log for anything that you like for this one, right? Second log negative 7.41. Yeah, that's it. That's all, folks.